Welcome back to the motorBench Development Suite video series. In this module, I will discuss how to measure motor parameters, tuning of current and velocity loops, and incorporating customization features into the embedded code once the motor and board files have been imported in the configure stage and the motor parameters are set. Let's talk about motor parameter measurement using motorBench. For motorBench Development Suite version 2.50, the motor parameter measurement is supported using the DSPIC33EP 256MC506 external op-amp PIM with the MCLV-2 board, which I have set up here. Before we open the MPLAB X IDE, I'm going to check the setup. I'll check that the PIM and external op-amp configuration board are in place, and they are. The MPLAB ICD5 programmer debugger is connected to the J11 connector and the PC, like so. The USB to RS-232 converter cable is connected to the J10 connector and the PC, like so. And our Hurst motor is connected into the M1, M2, and M3 terminals of the J7 connector. For this example, it does not matter the order in which the wires are connected, since we will be demonstrating a sensorless position estimator. Finally, I'll go ahead and plug in the 24-volt connector into the J1 barrel connector to power up the board. I see now that my board has turned on. For this demonstration, I have the MPLAB X IDE software open. To start the motor parameter measurement, first I'm going to open a file from the motorBench release collateral master here. I'm going to expand this folder, and I'm going to go ahead and select the sample-mv-33EP 256MCLV2.x project. I'll go ahead and click on opening the project. Then I will start MCC. So it may take a few moments for the MCC Content Manager window to load. Okay, so now under the Project Resources window, I can select the motorBench Development Suite. I'll go ahead and double-click on that. I'll close this package view and this Pin Manager grid view so that we can have a clearer view of the easy setup page. I'll also turn off notifications. I'll leave the output window open, and I'll expand this window so we can read a little bit. What I want to do before embarking on the motor parameter measurement is to make sure the MCLV-2 board is selected, which it already is. I want to make sure to import the appropriate motor. So we're using a 24-volt Hurst motor, so I'm going to select the Hurst 75 file. Once I select the motor, all the identification and nameplate parameters will populate. So before starting the motor parameter measurement, I want to make sure that the nominal speed, maximum speed, and number of pole pairs is established. I want to make sure that I have values for all of these specifications. Now I'm here at the electrical and mechanical parameter screen. I can see that there's some default values that have been set. I can either use these default values or I can use motorBench Development Suite to actually measure the values. And for this example, I'm going to do that. So I'm going to go ahead and click on Measure Now. And then a measure window will pop up. So under the self-commissioning settings for the COM port, I want to select the COM port that the RS-232 cable is connected to. So in this case, it's going to be COM6. The baud rate, for this example, I'm going to set this to 115200. And then I'm going to check the warning disclaimer here I don't have a calibration board connected. If there are some parameters that you need to calibrate before doing the motor parameter measurement, you can always refer to the latest motorBench user's guide to get direction and guidance on how to do that. But for this example, we're not connecting the calibration board. I'm going to check that I have connected a motor. And I'm going to use the default values for the motor parameters. And now I'm going to go ahead and click on Start to start the motor parameter measurement process. So I'll go ahead and bring the window down so we can see the values update. I'll click Start, and you'll see the message here that's building the self-commissioning project. So what that actually means is that it's downloading the firmware to the controller to do the motor parameter measurement. So it's going to connect through our ICD5. And as you can see in the output window here, it's starting to program. And as it's measuring, you'll see the values start to populate. And you'll also see the motor start to spin a little bit as the values are being measured. So this process takes a while, but you can see the values start to populate as the measurement continues. Here I see more indication that the values are being measured properly and my motor is actually self-commissioning. And another indicator here that the process is happening successfully is that on my RS-232 cable, I have an indication that there's communication happening between the program and the board using this particular cable. I can keep in mind that I can stop the measurement at any time that I want to. But for this example, we're going to continue it and wait until all the parameters are measured. And just another note, while this measurement process is happening, make sure that you have your motor clamped down because there can be sudden jerks or movements of the shaft that the rotor is connected to, depending on what type of motor that you use. So it's good to have this fixed down with a clamp of sorts, just so that your motor doesn't fall off your table or if it doesn't displace while the measurement is happening. We'll wait for that last value to update. If there are some parameters that are not as essential to have the accurate measurement of, I can always select skipping the measurement before I start. Okay, we can see that all the values have been measured. So I can close this measure window, and I see that the measured values appears in this column here in the parameters screen of the configure stage. I can click the Use All button to use all the parameters that have been measured. If I wanted to set these LD and LQ values, I could click on this widget here and enter the line-to-line stator measurements of the three-phase reference frame if I had an LCR meter. But for this example, we'll use the values that have already been calculated. I can go into my resource management window and I can click on Generate to generate the code. So that could take a few moments. Okay, we got a message here that the generation is complete. So now I can go back into the projects window. I can just go ahead and clean and build just to make sure that I can compile the software code. As you can see here, it's compiling and the build was successful. I can click on the Make and Program Device button here at the top. And I can download my software code to the board. You see here, you get the message that the programming and verify is complete. I can go ahead and hit now switch 2. And now we got the motor spinning. With the values that we measured. Let's talk about control loop tuning using motorBench Development Suite. The goal of tuning is to minimize error, reduce overshoot, and maximize the bandwidth. Improper tuning can lead to unwanted motor vibration, noise, and excess thermal dissipation, leading to earlier than expected motor failures, disruptions in end equipment operation, and potentially high maintenance costs. What I'm going to do to demonstrate control loop tuning is to just start a new project in the MPLAB X IDE. So I'll go ahead and click on New Project. It doesn't matter what I select for the family for this particular example. So I'll just go ahead and select any DSPIC33 CK device. So we'll do the CK256MP 508. We don't have a tool connected, so I'll go ahead and click Next. For purposes of this demonstration, we'll select the latest compiler, version 3.21, and then we'll give this a project name. So for the project name, we'll fill in the word tuning. Uncheck the Open MCC and click on Finish. Okay, so we got a new project open. We can now start MCC. We'll select Next here on the Content Type Wizard on MCC Melody. We'll wait for the configuration to complete setting up. Okay, once that setup is complete, we'll click on Device Resource, expand the libraries, and open up motorBench. Okay, the motorBench Development Suite window is open. So in previous videos, we talked about the Configure window, but we want to make sure that we have a board and we have a motor selected. So for this demonstration, we'll select the DSPIC33CK LVMC. It really doesn't matter for this example what board we select, but make sure that you select the appropriate board, whether it is one of our Microchip development boards or if it's a custom board. And then we'll go ahead and import the motor. But again, you want to make sure that you're either importing the correct motor, whether it's one of the motors supplied by Microchip, or if it's a motor that has a separate motor file that's been created. All the parameters here populate based off the content that's in the motor file. And so we can move on to tune. And so in this window, what you're going to see is that there are default values that are set. And these default values for the phase margin and PI, which stands for proportional integral, phase lag at crossover for the current and velocity controllers have been conservatively set to target system stability for a wide range of motors. So what that means is that you can basically use these parameters safely because they've been tested for a wide range of motors. If needed, these default values can be modified for better motor performance by either manually entering them in the text box, or you can use the sliders to change the values. Once I modify them, I can then review the corresponding magnitude and phase values of the transfer function in the Bodhi plot here at the right. I can also look at the changes to the proportional gain, and I'll go ahead and expand this window so you can see. And I'll scroll to the right a little bit here so we can see the full view. I can look at the changes to the proportional gain, the integral gain, and the crossover frequency here at the bottom of the window. So you can see that if I change the slider values for the current controller phase margin, I can see the values update here in the bottom, and then also the same for the velocity controller. I can also see the magnitude and phase values in the Bode plot get updated as well. I can also modify the X and the Y axes here in the magnitude graph ranges section. And I can also display the type of magnitude and phase plot for the current and velocity controllers by selecting open loop or closed loop. If I check on closed loop, I can see another plot show up here. And then if I click on, say open loop for the current controller, I can see another plot open up here, and I can see them side by side. So for more assistance and guidance on using control loop tuning, I can actually go back into the Easy Setup window. I can right click and I can select motorBench help. And it actually pulls up a navigator window where I can expand the Easy Setup, expand tune, and I can get more information on any one of these parameters. I can get more direction on how to actually set the values and some guidance on that. So keep in mind that when you're going through this tuning process, you can always right-click and go to motorBench help for more guidance. In general, careful tuning from default values can improve performance for most motors, but improper tuning can lead to poor performance and instability in the control loop. The field-oriented control section in the latest release of the MCAF, the Motor Control Application Framework documentation, has more information on control loop tuning, which can help to make tuning easier. The link to the latest MCAF documentation can be found by opening the release notes, which can be found in the Release Collateral Master folder. So let's discuss the different options available in the Customize window of motorBench Development Suite. So to start off, I'm going to start a new project. So I'll click on New Project right here. Make sure that Microchip Embedded and Application Project is selected. I can take a look at the dual inline module on the MCLV 48 volt 300 watt board. I'll check out what part number I'm using here. It's the DSPIC 33CK256MP508. So I'll type that in. .508. For the tool selection, I'll select the Curiosity Starter Kit. I'll hit Next, and then select the latest version of the XDSC compiler, which is version 3.21. I'll give this a name. I'll call this sample 48V. I'll uncheck the OpenMCC on Finish. Click on Finish here. Then I have my sample project. I'll click on the MCC button here. Then we'll wait a few minutes for the MCC Content Manager to open. For the content type, it'll be MCC Melody. So we'll wait a few moments while it sets up the configuration. Okay, we can go ahead and click on Device Resource, expand the Libraries tab, double click on motorBench Development Suite. Okay, now I got my window open. I'm going to go ahead and select the board. So in this case, I've selected the MCLV 48 volt 300 watt board. And then it auto-populates the DSPIC33CK256MP508. Now for the motor, for this specific example, we're going to import a motor that's not part of the standard motorBench release package. So I'll go here to my desktop, and I'll select this motor file. I'll open it up. And then we'll use all the default values that have been defined according to this motor file. I'll go ahead and click on Tune and use the default values, and then click on the Customize window. So depending on the motor control implementation, I'm able to set the settings based on current measurement method, position and velocity estimators, and additional operating parameters. At the bottom of it, which I'll scroll down to and show here in the advice section, there's guidance on how to set the commutation step and ripple current. There are default values already entered that will work for most motors, but they can be modified depending on the motor type and the level of performance needed in the end application. In general, the MCAF, the Motor Control Application Framework User's Guide, provides detailed guidance on setting up each of these custom parameters. So for purposes of demonstration, I'll show you how to set up censored FOC control using the MCLV 48 volt 300 watt board and a motor with an encoder connection. So I can show a little bit of the setup here. We've got the 3-phase wires connected to this connector here. We've also got the encoder connections connected on this connector right here. So we establish those connections by looking at the data sheet and making sure that they match up with the right pin assignments on this connector. So you can look at the data sheet for the motor. You can also look at the user's guide for the specific development board that you're using in order to match up correctly the wires with their correct inputs here on the connector. In this case, it's an encoder, but if you were using a Hall sensor, you would connect to this particular connector. So for this demonstration, we're going to set a few values here in the Customize screen just to give a feel of what this window can do. So in this case, the current measurement method I've set as triple channel. For estimators, I've set the quadrature encoder. And if I expand parameters, I can enter in the number of lines. For this particular motor, it's going to be 1024. And then the synchronization method will be set as a line sweep. I can go down to the additional active estimator section and select quadrature encoder. And then I'll go ahead and leave the rest of these parameters at their default values. So now I'm ready to generate my code. I'll click here on MCC, click on the generate. I can click here on the user output screen. I can see that the generation of that code has been completed. I'll go ahead and clean and build. I'll expand my output window here. Just make sure that we try it again. Okay, the build is successful. Perfect. We can right-click here, go to Properties. We can make sure that our hardware is connected just as a double check. Then we can click on Make and Program Device Main Project to download the code to the DSPIC. It's connecting to the programmer and downloading. You can see the programming and verify complete message here. So now I'm going to go hit the button, and I can see that my motor is starting to learn its positions. So it's going to do a couple of rotations and it's going to start spinning. And I can turn the potentiometer to change the speed. Then I can press switch 2 here to change the direction of it. Again, make sure that your motor is clamped so it doesn't make any sudden jerks or movements. Then I can press this switch here to just stop the motor. In our next video, we will discuss the custom board support feature of motorBench Development Suite.